Hey, welcome to 6502 Emulator Part 5 in Python with Tokyo EdTech. That is me. In this installment, we're going to be taking a look at the jump command, which allows us to jump to another section of the code. This is what gives us the ability to make a loop, so we're going to do a simple loop. There's two addressing modes for this, absolute, which we've already done, and there's another one called indirect, which we'll try to implement today. And then we want to do something with wrapping the values. What that means is like with INX or DEX, INY, DEY, when the X register gets to 255 and you go up one, that's 256, but you can't actually do that in 8-bit, in an 8-bit computer. You need to wrap it around and it actually goes back to 0. Same thing when you decrement, so you're at 0, you subtract 1, that takes you around to 255. As a reminder, this is live coding. I don't have this planned out in advance, so there's some rough spots and things I'm trying to figure out how to do on the fly. Hopefully, you can kind of see. You don't always know what you're doing when you start a coding project. Sometimes you do something and you come back to it, you're like, oh my god, why did I even consider that? Anywho, let's get into the jump command. So I'm gonna go ahead and take a look back here at the website. You can see here it says jump, and it transfers program execution to the following address or to location contained in the following address. So there's some other things here about the last byte thing. We're just going to completely ignore that. I think that was actually a bug in the code or something. I think it was actually a bug, not in the code, but in the processor. So anyway, we got a hex code 4C. It is a length of 3. And, well, it's absolute, so it's going to be 3. So let's go ahead and see if we can get 4C working. So I'm going to go back to my code. I'm going to go up to, or down to, I guess, to where all our commands are. I'm just going to go ahead and make a new section here. I'm going to paste that in. And don't forget, this is hexadecimal, so you add the 0x prefix. And again, now that I've done this, I'm like, okay, maybe I should have done this a different way. I probably should have made a class for the instructions. A couple things I realized I probably didn't make a good choice at the beginning. Now I could change it now, but it's our purpose here is really just emulation, not perfect coding. And that was absolute mode. So absolute. All right. So we've created this self.jmp, which is jump. And so then I need to create a command down here for jump. I need to say a method, and I'll just try and keep it in the same order that I've done it. So I'm going to go jmp and def jmp self and mode. So again, I'm assuming you've come from the last tutorial. You know what I'm kind of doing here. If not, you need to go back and probably watch some of that stuff. Now it's been about a week since I worked on this, so even I'm a little bit like, what exactly did I do? So I'm gonna go ahead and copy this because this is gonna be basically the same for almost all of our, all of our commands, except certain ones like setting flags and things. But anytime we're using some sort of memory location. So since the mode is going to be absolute, it's going to get us the location by mode. So that's already taken care of for us. So what do we do with that location? And what we do is we actually just set the PC counter to the location. Oops, LOC. That's it, easy peasy. Okay, so I'll go ahead and put that in a comment. So set PC to LOC. Kind of obvious there, but let's go ahead and comment that anyway. So I'm going to go ahead and create some testing code to see if we can get this to work. Where's the, oh, that's right, I separated it out into system. Now what I'm going to do is I'm going to go ahead and just basically copy all this stuff out of here, and actually I'm going to keep LDA because I'm going to need that, but I'll copy all this stuff. I'm going to cut all this stuff out. I'm just going to put it into a separate file, and X, and I just call it scratchpad.j or .py. But I do want to keep this. I'm going to go ahead and do LDA. I'm going to put that back in here. And so what I'm going to do is I'm going to load the accumulator with 0x. We'll do F0, and then F0. And did I do? Let's see if I can get that out here. Variables. did we do TXA? Yeah, we did. Okay, great. So I'm gonna load F0 into the accumulator. I'm gonna do. Let's go ahead and just write it out quick. I'm gonna do TXA. So I'm gonna transfer TAX. TAX. So I'm gonna transfer what's in the accumulator over to X, which will be F0. And then I'm gonna do CPU.push. I'm gonna do INX. And then I'm going to do CPU dot, I'm going to do debug, which is the special opcode we created, dbg. And then I'm going to do CPU dot push. I'm going to do jump. And I'm going to show you how we're going to do that in a second. It's going to take a little bit of calculations, but let me finish this first. So let's go and get our opcodes. I think it's easier to go here. Control find, and I could have done this ahead of time, but I didn't. Oh, that's great. That's really helpful. Let's go ahead and do TXA, which is, no, wrong one, TAX. So that's AA. So I'm going to go back and do 0xAA. I actually created a little basic, very basic assembler, but I don't think it's ready for prime time yet. So we'll come back to that some other day. We got INX. This is E8, so that's good. That's there. 0xE8. And what was debug? DBG. Let's get that from Scratchpad. 0x42. Oh, I know why I chose that. Because of Hitchhiker's Guide to the Galaxy. 0x42. And now let's go ahead and do jump. Okay, so jump. Let's go back. Well, I forget what it was already. I'm getting older and my memory is not what it used to be, especially all these numbers. So let's go ahead and do jump, which was 4C. All right. So 0x4C. So now the next 2 bytes are going to be the location that we want to jump to. Okay. So in this particular case, what we want to do is we want to jump back to this line of code. So what we're gonna do is we're gonna store F0 into the accumulator. We're gonna load it. We're gonna transfer that to X, and then we're gonna add to X, and then we're gonna jump, 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 jump. Okay. So this would be an infinite loop, except we're only gonna, like in the code, we only tick 100. I'm gonna actually lower that down because it's annoying. It's gonna make it 30 just for now. Okay. So to calculate this location of INX is I'm going to start at 1000. So this is 1000, 1001, 1002, 1003. Okay. So remember, it's in the opposite order. So remember, it's the least significant byte, in this case 03, so 1003. So let me calculate again. 0, 1, 2, 3. So what's going to happen is we're going to load the accumulator, transfer it to X, increment X, so we should see F1 when we debug. Then we're going to jump back, F2, F3, F4, F5, F6, F7, until the loop ends. So let's go ahead and see if I did this correctly. Hopefully. And let's run the system. Okay, so far so good, no errors. So we see X is 1, which is not what we wanted, I think. Oops. Okay, command 3 not implemented. All right. I know I did wrong. Do I know I did wrong? Absolute 04C. Okay, so what happened is... Oh, I know what I forgot to do. Okay. Do I? No, I don't. Did I spell something wrong? Absolute, o.absolute. So it's not jumping as far as it should jump up 3. Oh. Oh. I know what happened. All right, let me explain what's going on. Okay, and this is the consequence of a design decision we made, or we, I should say, I made earlier. So yeah, all right. So if you recall, uh, based on the mode, where's that at up here? Yeah, based on the mode, we updated the program counter. Okay, so we're jumping, but then we're also adding. We're jumping back, but we're still adding the 3. Okay, so we got to think about how we want to do that. Um, yeah, I'm gonna think about that one for a second. Um, okay, I'm just gonna come up with a non-ideal solution so we can get through this. Maybe we'll revisit that later. So what happens is we set the program counter back, but it was wrong. Okay, so let's go up here. Let's see what we got here. Where do we have that? Okay, so we have this thing self increments. Okay, so what I'm going to do is I'm going to subtract the increment because the other part of the program adds it. So we'll subtract the increment. The other program adds it, and they will cancel each other out. So let's see if we can do that. So let's go back to our jump command. So before we set that, we got to set PC to the location minus the self.increment. Increments? Or is that part? Or is it just increments? Increment. Let's go back up here. That's part of the CPU. So it is self.increments. Yeah. Self.increments. Sure, I didn't pop up. Mode. Okay. So no matter what the mode is, we'll be fine. So what happens is it executes the command. We set the location to the actual location minus, the increments. When it returns, it's going to re-add that increment, and that should give us what we want. Let's try it. I think that's what we want to happen. Or maybe not. System. Let's implement that. Okay, there we go. Let's see what we got here. Now we're running out of space on the screen here. It's kind of annoying. So X is 1, 2, 3, 4, 5, 6, 8, 9, 10. So far, so good, except for something went wrong with LDA. Is that LDA indirect? Is that the wrong LDA? Let's go ahead and see. LDA. I bet that's the wrong LDA. That's 0 page. All right, we want immediate, so it should be 0xa9. All right, xa9, and that, yeah, duh, number 0xfo. Okay, now let's try it again. Okay, so now we got 240. We transfer, so I guess F0 is 240. Transfer that to X, which is 240. Transfer it to X, 240. We added 1. Okay, so, and then we got that. So let's go ahead and 242, 3, 4, 5, 6, 7, 8, 9. Okay, it's working. I think I'm pretty happy with that. Let me go ahead and change this to FF. Okay, and this is what I want to show you. The program would be stuck in a normal loop, but we just decided to end it early. So let's go ahead and run that. So notice how we went from 255 to 256. Okay, so this is because in Python, you can add whatever you want to the variable value. But because we're emulating an 8-bit computer, we need to wrap that around to 0. So let's go ahead and do that. So what I'm going to do is I'm going to create a command in my little CPU here. And let's see here. And there must be some place where I put all those at. Also, my mouse isn't working. So I use the stupid trackpad. Okay, so we have these different commands here. Let's put that with this. So I'm going to go ahead and make a command here. Call it def wrap. Call it wrap for now. Value. And what we want to do is, so we're going to go ahead and wrap 8-bit values. I might call it wrap 8 later. I don't know. We'll see. We'll see if we need that. So what we can do here is if the value is greater than 255, value equals value percent 256. So the modulus, what that does is it divides by 256 and gives the remainder. So if it's 256 divided by 256 is 1, and there's 0 left over. So that'll wrap it around to 0. If the value is less than 0, we can just add 256. So if we have -1, we add 256, that gives us 255. Now it doesn't protect us if the value is like -10 million, but let's go ahead and leave it at that. Okay. And then what we'll do is we will return the value. Okay. So now what we need to do is test this, but let's go to our INX command. That's the one we're testing right now. So self.x equals wrap self.x. So for any time that we, basically add to the x or subtract from x, we need to put this command in. Okay, so let's go ahead and test that, make sure it's working. Okay, run the system. Okay, and it should be self.wrap. Of course it should. All right, that's good. Okay. So now we got 255. And if you remember, it was 255 plus 1 was 256. Okay. So let's go ahead and just change this to 0F. Let's do FC so we can actually see it in action. Yeah, I started writing some tests for this, testing code, but then I was like, oh, that's a lot of testing, and I got bored with it. So I just decided to just do it this way. Okay, so we start with 252 in the accumulator. We transfer that to X. We increment X, and then we got debug. So we're here. Then I'm going to hit enter, and we're going to jump back to INX and just repeat that. So we'll see 252, 253, 254, 255. Now we're going to wrap. Goes to 0. Okay, so I'm pretty confident that I did that correctly. So what I want to do now is I'm going to go ahead and update the code for INX, etc., etc., etc. So where is that? So we have INX. So all I gotta do is just update the code for all of them. And I know I'm gonna mess this up, but so same thing for DEX. Now I should test it, but there's only so much time in the day. So don't forget to make this Y. So anytime you have this type of change to a register, we got to make sure the values wrap the way they're supposed to. And you might think, well, do we need to do this with TAX? And we shouldn't need to do this with TAX because as long as we're wrapping it correctly, it should work how we expect it. Okay, so it's only when we're incrementing or adding. And now with those registers, we can only increment. We can increment or we can load a value. And as long as the rest of everything's working correctly, that value should be consistent. I should probably check DEX. All right, let's go ahead and check DEX just to be precise. DEX. Where is DEX? Did I do DEX? Well, didn't do DEX. Go figure. What's here? DEX is here. Is it up here? Or am I just missing it? Oh. All right, let's go ahead and add DEX and DEY. Oversight. Okay, DEX is CA. Is X0XCA. And DEY is 88. 0x88. All right. And this is also implied mode. And this should be DEX, and this should be DEY. All right, so CA is DEX. So let's just go ahead and test it. We have some time. DEY, so let's go DEX. So that was DEX was CA. All right. All right, so let's go ahead and run this. Let's just see if it goes down. 250, 249, okay. So it's going down, that's a good sign. So let's go ahead and load this. Instead of FC, we'll load like 2. 0, 2, 0, 2. Alrighty, let's try it again. Okay, so we know 2 and we DEX, so we subtracted 1. We're at 0, and we should wrap around the 255. Genius. Okay. Again, now, if we had time and all the time in the world, we could test DEY, etc., etc. Like I said, I did start writing some tests, but I kind of just realized that was going to take hours and hours and hours and hours and never really be done. So we'll just do it this way. Anyway, so let's take a look back here. So we've done so far is jump absolute. We've done wrap values, INX, DEX, INY, and DEY. And also, I should add, implemented DEX and DEY. We had the methods, we didn't have it in the list of commands. So I guess that's good. So let's take a look at indirect mode. This is something we haven't done before. And so let's go back to here. We'll go back to jump, just to explain what indirect is. So you notice how how you put it, the way it's written in parentheses. So what this does is, instead of jumping to 5597, it jumps to the memory address stored at 5597. Okay, so it reads the values at 5597 and jumps to there. Okay, so I'll explain that as we go along. So we need to implement a new addressing mode. So let's go ahead and take a look at what that looks like. So this is indirect. I'm just going to add auto. We're going to go down to here. We'll do that part in a second. Well, I guess we can do it here now. It's up on the screen. So it is 6C. So this is 0x6C. And this is going to be indirect. Okay. And the increments for that is also going to be 3. So mode.indirect 3. Okay, and that just came from here, so that's the length. All right. And so then what we need to do, and because we did structure the code a certain way, we have this method, where is it, like get location by mode. So we're going to go ahead and going to copy absolute because it's very similar to absolute. I'm going to keep it in the order that we've been doing it. So, okay, so this is indirect. So this is where it gets a little confusing. Okay, so let me think this one through. So it's the memory. Wow, okay. So it's going to be self. Yeah, dot memory. Yeah, I think this is right. So it's the value stored at the location referenced in the next bytes. Oh my gosh, that's crazy. Um, so that's pretty cool. I'm pretty happy with that. I think that's going to do it. So again, well, you'll see when I do the testing code. So this is going to be a little more. This is going to definitely get more complex. So what are we going to do here? Okay, so I need to do store A. So let's go ahead and get back to here. Okay, so when you see the testing code, you'll understand it a little better. Store A, STA, where's that? Okay. So we're going to do 8D. We're going to store absolute. So I'm going to copy that. We're going to CPU.push. What we're going to do is we're going to store A in 0x. We'll put it in. We'll just put it in 2000 just to make it easy. Okay. And that is 0x, Control V, and CPU dot push. Yeah. Wow. Okay. So again, least significant byte is 0. CPU dot push 0x20. Okay, we're going to store that there. Okay. All right, this is complicated. Let me finish this part, and then we're going to do this again. Do a lot of counting here. We'll fix that in a second, and this is going to go in 2001. Oops, 0x 2001. Alrighty, this is pretty exciting. Okay, and then down here, our jump is going to be, where was that? Jump. 6C, that's right, 6C. All right, in this case, it'll be 6C, and it's going to be 2000. Oops, 20. Jump, 0x. Alrighty, now, here's where this is crazy. All right, so what we're going to do is we're going to store the location where we want to jump to in this location, 2000. Remember, it's 2 bytes, so it's going to be our least significant byte and our most significant byte. All right, the location we want to jump to, we're just going to jump to the same DEX. Ooh, I gotta bring in the LD. I gotta bring this back. Okay. All right. So we still want to jump to here, but instead of calculating this exact, I gotta calculate it now. But instead of calculating this exact value to jump to, I'm gonna put that value in 2000. So let's go ahead and count, just like we did before. So we got 1000, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 goes to A, B, C, D. So this is location 100D. So that means we got to store up here 0D and 1000. And here, this is going to be 1000. Wow. Okay, so 0D SB of 0x 1000D. Alrighty, and this is, and we're storing that in location 2000. Then we're loading the 10 part. This is complex. 10. Okay, and we're loading that into the accumulator. We're storing that in 2001 location. Then we're going back to our original program, which was load the accumulator with 2, transfer A to X, decrement this. This just says this is at location 10Z we calculated. Debug, and then we jump to whatever the memory location is that's stored at 2000, which is 100D. So this is a way of, indirectly jumping. So you can create jump tables and things like that. So, all right. Wow, if this works, I'm going to be really impressed. Okay, so we've got 2, 1. So if it's working correctly, it's going to jump back to the same location. So you see the same output. Oops, something went wrong. All right, something went wrong. It's like C2000. Unless, okay, let's see here. So we got to here. So everything was working fine to here. So the jump's not working. All right, let's just make sure the numbers are correct. So 0D, we store that in 2000. 10, store that in 2001. Okay. Load TX, okay. Debug and jump. All right, let's just make sure we count it correctly. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 12, 11, 10. That's A, B, C, D. Okay, so I'm confident that's pretty correct. So let's go ahead and take a look at our jump code. Because the problems, it's either here. That's probably here. Let's go back to jump, just make sure. Yeah. Okay. Get the location. All right. So it's got to be in there somewhere. So I'm doing something wrong. Mode equals indirect. So it's just self. So okay, I know what I did wrong. Okay, so this is calculated wrong. Because this is self memory. Got it. Okay. Oh my gosh. Okay. All right. This is wrong. So basically, what I was doing is I was accessing. This would be like this was because this is the least significant byte, but I need the least significant byte. Okay. So I was accessing basically the 0 page. Okay. So that is completely wrong. So we have Ellis. All right. Now, what's definitely a better way to do this. I mean, basically, it's going to be like this. It's going to be times 2x plus okay, got it. Let's just undo all this. All right. So Okay, so basically what we got to do is we got to find the location. Okay, so for example, the starting location is going to be two. So in this case, so let's say it's going to be 2000, right? So then, got it. So then from that, we get the LSB. Okay. Wow. Okay, so then the new LSB equals self dot memory LSB. No. Location. Okay, this will work. Okay. MSB equals self dot memory location. And then the new location equals the same thing. All right. There we go. Okay. That's a good thing we checked it. We called it, tested it. Okay, so put a little. Okay, get the memory location. Memory location where jump JMP address is. Okay. Get the jump address from the memory location. All right. And it should be location plus 1. All right, I think it's gonna work. Let's test it out. Okay, so we got that. 0, 55, 54, 53, 52. I'm happy with myself right now. I'm so glad that worked. Anyway, it's a great feeling. So let's go back real quick to take a look at our coding concepts. All right, so what we implemented today was the ability to jump to a location in memory. So basically what this lets us do at this point is that we can make a loop. So once you have a loop and you can manipulate numbers, you can do almost anything in coding. The only thing we don't have right now is comparisons, and that's going to come in a future video. But we implemented the absolute mode where we jump to a particular location that we already know, and we implemented indirect jumping, which we do to a location that's stored in another memory location. You saw that process and how that played out incorrectly at first, but got it in the end. And then we made sure that because we are on an 8-bit computer, we are wrapping our 8-bit values. So when we hit 255, we go to 0. When we hit 0, we go to -1. There is no -1. Technically, you can't do negative numbers in binary. That's a future lesson. But we wrap around to 256. So let me just show you real quick the code again, what we had to add to make those things happen. And so we had to add the indirect mode. We had to add the commands here. So we had to jump down here at the end, and we also had dx, dy. I just forgot those. So we have our absolute and indirect modes. We have the number of bytes that each command takes care of. We had to subtract, if you remember. Well, there's the wrap code. Okay, so you didn't see that earlier. You can pause here and write that down. So we go over 255, take the modulus. We go under, just add 256. We did in the jump command, we had to do this offset for the increments. Okay, but otherwise, it was pretty straightforward. And then in the mode command, again, we didn't structure this badly. Again, I might have used classes or something a little bit more, but I'm pretty happy with this. And then this was that little monster of the indirect, where we had to get the memory location, the start of the least significant byte, and put that into location. Then from that, get the new location and jump to that. So yeah, that was that. Anyway, that was part 5. That was a big one. Hope you enjoyed it, and like, subscribe. As I like to say, keep on coding.